join me on page 222. We're going to do a little bit of calculations today. I made a point of, actually I think that one's mine, Cole. I made a point of changing some numbers so that you didn't need calculators, although I'm sure that many of you have a calculator function on your phone. Page 222, as it says up on the screen. You might remember the little Harry Potter video we showed yesterday. Yeah, we watched the entire Sorcerer's Stone. Kristen, too bad you missed it. And I gave everybody answers to the exam and a $20 bill for lunch. Yep, that's what I did. Didn't I, guys, right?
Yeah.
See?
Yes.
So there was a Harry Potter video where the cat turns into the teacher, and some nerd decided to make a video about it, saying that it was impossible because the cat would only weigh about maybe 5 pounds, and the professor weighs like over 100 pounds, so matter could not be destroyed for that to happen. So I'm going to sort of do my own little thing here, based on page 222, conserving mass. In investigation 6.2, you saw that when two solutions react to form a solid precipitate, the mass stays the same. Is the mass constant for other types of reactions? Are there any other reaction where mass is gained or lost? In some chemical reactions, matter may appear to be destroyed. For example, you might think that the burning of a forest fire or forest destroys matter, reducing the trees to a mere handful of ashes. Is the matter destroyed in a forest fire? Where does it go?
It goes in the air.
Yeah, the matter is not destroyed. The carbon is converted to gases and releases into the atmosphere, right? So there would be water vapor, there would be carbon dioxide. All of the matter of that tree is basically reduced to a pile of ashes, and then all of the gases that are then released into the atmosphere. Here's an interesting thought to think about. Hold your index finger up. Okay? What's in there? What's in your finger? Cells, which are made of?
Bones.
Atoms. Okay, so where do those atoms come from? Before you were here, I don't think there's anyone in the room, with the exception of the two adults that are over 20. 20 years ago, where were those atoms?
And a monkey and an alien. No, you know.
Okay? 20 years ago, you didn't exist. Where were those atoms? Maybe in some food product somewhere.
Chris Serling is 20 years ago.
Yeah.
He's still in school, though.
Thanks for sharing. Say 50, 60 million years ago, where might those molecules have been? In a dinosaur? Some of you, I would agree, probably, yes. Possibly, right? So yes, your atoms have been conserved over the years. You might have been part of a monkey, a dinosaur, perhaps an alien, maybe. Maybe you came to this earth, the molecules that make you up, maybe came in an alien. That would certainly explain a few things.
No. The alien equals human.
Sure. All right, so next paragraph. For more than 200 years, scientists tried to devise methods to trap the gases that were used or produced in reactions and to find ways to measure their masses. We were lucky yesterday. We have electronic scales that would measure up to 1/100th of a gram. 300 or 400 years ago, they didn't have that, right? They couldn't measure that accurately.
They probably could, but...
And even still, what we used yesterday, we still lost some mass, right?
Yeah.
So after years of experimenting, scientists agreed that the mass is neither gained nor lost in a chemical reaction. This conclusion is stated as a law. And a scientific law is a general statement that sums up the conclusion of many experiments, or a statement that summarizes an observed pattern in nature. So I'm just going to sort of just get that out of there. So a scientific law is a general statement that sums up the conclusions of many experiments. It's basically been proven, right? It's accepted as fact. General law, accepted as fact. You could say also, it states that a pattern has been observed. We have observed many times that in a chemical reaction, mass is conserved. Here's an example of a scientific law. What goes up comes down, right?
Gravity.
Yes.
If I take a tennis ball, I'll use one of these here, right? And when I toss it up, of course it
Hit the floor.
Go
Blow up a balloon and then I'll prove you wrong.
What if, wouldn't it be cool if I had Jedi powers and one of these days I could break that scientific law and just say what goes up and it just
A
stayed
balloon.
up? That would be cool, wouldn't it?
A balloon.
Helium eventually comes down.
Helium will leak out.
Yeah.
They shoot a rocket in the sky, keep going.
Only if you have a greater velocity than escape velocity for the Earth, which is about 11.2 meters per second. Sorry, 11.2 kilometers
I
per
know, but
second.
if the rocket goes up the planet, like to this planet, it's never coming
I
back.
could-
That is only true if the rocket has an unlimited fuel supply, right?
Nah.
If it doesn't have unlimited fuel, it has to escape. It has to get to a spot where it has that escape velocity. When they send a rocket to the moon, because it has so much fuel, they can get it to a velocity where it will actually escape Earth's gravity and keep going. I think escape velocity from the sun is well over like 300 or 400 kilometers per second.
I could run that.
You just did, right? You just did and came back, right? Yeah, that's what I thought.
No, they didn't.
Never did do it.
Nobody went to the moon.
Yeah, they did.
All right, so moving on. The law of conservation of mass states, and this is what we found out yesterday, Dylan, right?
What?
The law of conservation of mass, this is what we were working with yesterday. The law of conservation of mass states that in a chemical reaction, the total mass of the reactants is always equal to the total mass of the products, and that's exactly what I've got right there. In a chemical reaction, the total mass of the reactants, Mike, which you're on which side of the arrow?
What arrow? Not even an
There
arrow.
isn't there, but in a chemical equation, word equation, where are the reactants? It's either left or right.
Left.
Correct. And what's on the right? What's that called?
Product.
Products.
Oh, you're right.
In a chemical reaction,
You know what, Chris?
the total mass of the reactants is equal to the mass of the products. Alrighty. Since the mass of the products is always the same as the mass of the reactants, what does this tell about the atoms that make up the reactants and products? Are the atoms the same atoms?
No, yes.
And the answer to that is yes. Atoms are not changed nor destroyed. I think I spelled that wrong. Yes, I did. Only the arrangement is changed. The atoms are pulled apart, the molecules are pulled apart, and then put back together a different way. Okay? But they are all still there. And that's that whole thing about balancing equations. I think what I need to do is give you guys something just to play with all the time,
It was
eh?
just stressful. You
Yeah?
don't
Yeah,
wanna-
they wouldn't get thrown around at all, would they?
No.
No, not at all. Yeah.
Yeah,
Play-Doh. It's not a terrible idea. Okay, here's an example. I'm just going to go off the book here a little bit.
Go off the chart.
Oh. Okay, so for example, and we've talked about this already. Listen, okay?
Before you hurt yourself.
Okay, I'm going to start showing you how to do stuff that you're going to have to do later. Okay?
Why do you
Excellent.
always single me out?
Because you're the one that always asks, I don't know how to do this.
No, you don't teach it first.
Maybe you should listen. We'll try that first.
Okay, we'll start there.
Okay, so we've seen this equation before. We've seen methane plus oxygen gives us water and carbon dioxide. There's the methane. There's the oxygen. Where would the oxygen come from when you burn methane? From the air, right? From the atmosphere. Would give us H2O, water, and CO2, carbon dioxide. The number of atoms on each side must remain the same, and this is what we call a balanced equation. We've been looking at these quite a bit. Is this a balanced equation right now?
Wait, I have to look at it.
Dylan, look at this equation. Is this a balanced equation?
No,
No, why not?
because,
What's wrong?
I don't know, it doesn't look great.
Doesn't look right.
There's a 4, and then the rest of it.
Yeah,
Well,
that's
there-
what we would do.
Okay, so there's 4 hydrogens here, and there's only 2 there. So we could agree that this is,
Incorrect.
we'll say unbalanced. Right? It's unbalanced. We refer to that as a skeleton equation.
Put an X through.
No, it's nothing wrong with it, right? It's just not balanced. That's all. Okay. Now, here's a little bit. Okay. So, here's a little bit of an environmental thing to think about when we talk conservation of matter. Okay? When you go for a drive and you burn that gas in your car, where does that go?
In the air.
In the air, right? How much do you think How much do you think a tank full of gas would weigh?
4 to
Oh,
3
okay.
kgs.
4 to 3 kgs. Which means you went 4 to 3. Not 3 to 4. Most people go, yeah.
3 to 4, whatever.
You saw it up there, did you?
No.
Oh.
It's lucky gas.
Okay. Each kilogram of gas mixed with oxygen produces 3 to 4 kilograms of water vapor and other gases. So every kilo of gas that's in your tank actually produces about 3 to 4 kilograms of water vapor and other gases. Now I just spent 10 minutes telling you that matter is conserved. How can 1 kilogram become 3 to 4? No,
Magic.
no. How can 1 kilo of gas become 3 to 4 kilos of water vapor? Yeah, it's mixing with oxygen. So how much oxygen would be needed if I should have had each kilo, 1 kilo, let's just say that it becomes 3.
That's the carburetor.
How much oxygen would you need then? You'd need 2 kilos of oxygen, right? So actually, when we're driving our cars, we're burning up oxygen in the air, oxygen that we could be, using to, breathe.
Breathing's overrated.
Yeah, I would agree. Sweeping and curling, same thing, right?
Yeah.
Yeah.
We are keeping.
Okay. Did you know that a gallon of gas weighs about 6 pounds?
Don't tell me something I already do.
What's going on there, Nathan? Oh, okay. 1 gallon of gas weighs about 6 pounds. So that means if you have an 80-liter tank, I know I had an old van a few years back, it had an 80-liter tank in it. How many gallons is 80 liters?
18 gallons. Of
You're correct. It is about 18. About 18 gallons. So if you, fly to Winnipeg and back and burn up a whole tank full of gas, you're talking about 108 pounds of gases into the air. 108 pounds of gas.
That's pretty bad mileage.
That's like almost.
That has nothing to do with mileage. That has nothing to do with distance.
You say you're going for Winnipeg.
Well, there and back.
That is distance.
Yeah, there and back.
You said
I
it
think
has
you'd be
nothing
hard
to do
pressed to get there and back on less than 80 liters. Erica,
You get
pay
there and
attention,
back
please.
in like less than 4 gallons.
Yeah, I don't know. But my point is that when you burn up that gas, it doesn't just disappear, like gasoline. When you burn up that gasoline, it doesn't just disappear, it actually goes into the air. Everyone's doing it.
Exhaust. You know that. How many liters?
But it doesn't disappear. It doesn't disappear.
Like 5 liters of oil. Wait.
I just ride a bike or walk.
I don't know. I think it would probably weigh like motor oil kind of thing. Does it weigh less than gas? Is it less dense?
No.
Would it float?
It floats on top of water.
Yeah, I know it floats on water, but would it float on gasoline?
Yeah.
No, because you mix it. It should be mixed gas.
Yeah, I know, but doesn't it separate eventually? Mixed gas? No? Okay, then it would be about the same then, I guess, right? So how much did you say? How much oil? 5 liters, well, 1 liter, 8 liters is about 18. 5 liters is about a gallon, right?
Two.
And I'm thinking that it would be about, so it'd be about 6 pounds, roughly, right? Okay, here's the part where I'm going to actually show you what we're doing today. Here's this, if you're not writing stuff down, you might want to start with this. This is what you're actually going to be doing today.
So you need to write this.
Yes, Christian, write this down. This is how, I'm showing you now the how to do it part. So, if I've got methane burning with oxygen, giving us water and carbon dioxide. If I have 60 grams of methane, Christian, here's the part where I show you.
Yeah, Christian.
Sorry, Chance, here's the part where I show you.
I wrote
60 grams of methane reacts with 120 grams of oxygen. Because matter is conserved, how much water and carbon dioxide do I have at the end?
Like
60. Ken, I need you to watch
You're
now.
gonna have
I
180.
need you to watch.
180.
like 180.
180 grams, exactly. Really not that hard. 180 grams of the two together, right? Not a problem. If there's 100 grams of water, how much carbon dioxide is there? If I have 100 grams of water, then I would have 180 minus 100, of course, 80 grams of carbon dioxide.
Was that Y or G?
G, 80 grams.
No, that's the 100.
Yeah, grams.
Not really.
That's all we have to do for this thing?
That's all it is, right? It's just making sure that the mass on the left is equal to the mass on the right. That's all it really is. Okay? Let's have a look at the next one. Again, if you want to write it down, be my guest.
Okay.
If you don't, also fine, but you better be able to do it. Excellent. This time I've got 25 grams of carbon dioxide reacting with 20 grams of oxygen. How much CO2 does it produce? And I want you to write the balanced equation for this reaction. Maybe we should write this one down. I'm going to bring in the balanced equation stuff too. I'll give you a second to jot it down. What looks different between here and here?
They don't have that thing.
No word equation, right? Okay, so we're going to have to do that part. Here I have 25 grams of carbon monoxide reacting with 20 grams of oxygen. How much CO2 does it produce? So carbon monoxide is what? CO, carbon monoxide, CO, and we're reacting with oxygen. Oxygen is
O2.
O2. How do you know it's O2?
Because I'm smart.
Yes, you are. How does a smart person know that it's O2 and not just O, Christian? How does a smart person know to put the O, the 2 back there, Christian? It's a diatomic gas. It's one of those diatomic gases. It's O2. How much CO2 does it produce? So it's going to be CO2, which would be, what would be the name for CO2?
Oxygen.
CO2, carbon dioxide. There's my word equation. I've got 25 grams of carbon monoxide, 20 grams of oxygen. How much CO2 will it produce? No calculator needed, I hope.
50. What?
Like 45.
45 grams. Right, Mike? Yeah, good, makes sense. 45 grams. How do I write the balanced equation for this? Is this balanced? Oh, I picked an easy one, didn't I?
No.
It's not balanced?
I think it is.
Why do you think it is?
It just needs
The numbers equal up.
1C, 1C.
Oh.
2 O's, 2 O's.
Oh,
Right? That means that every molecule of carbon dioxide reacts with 1 molecule of oxygen and produces 1 molecule of C. Oh, hang on a sec here. Is this balanced? You guys are leading me down the garden path. It's not balanced.
Oh, no, it's not.
It's not.
I told you.
We better do this here. C and O. 1C. I was sort of like, yeah.
Trying to get all
Maybe I did that on purpose. How many O's on the left?
3.
One. Here we go. 3,
1, 2, 3,
2.
2. Okay. What do you do when you've got one of those 2 and 3 situations?
You gotta just go to
You got to make them into
6.
6, right? That's the only way the 2 and the 3 are both going to be the same, by making them 6. So how do I make 6 on the left? Do I just change this 2 to
That's the
a
right.
6?
That's the right.
The right, yeah.
You put a 3 in front of
To
it.
put a 3 in front. Remember, you can only put numbers
Sorry for the
in front.
interruption. Could the following students please come to room 287? Matt Kimach, Justin,
The purple monkey.
Okay. I'm seeing a couple of shaking heads back there. This isn't going to work because now what's going on here? I got 6. I'm good now, aren't I?
No.
Uh,
Wait, yeah.
Well,
No.
now what?
No.
Now I got what?
3 C's.
3 C's. Uh-oh. So what do I? Well, I guess I'm going to have to do this, right?
Yeah.
And now,
Oh, now you're gonna have a 4.
Now I don't have 6 anymore. I got 3
9.
and 1. Well, now I got 5, right?
Yeah.
So what should I do?
Wow.
How many are you guys?
I didn't do anything.
How many C's have I got right now? Let's start over again. I got 3 C's, 3 C's. Okay. 3 O's, 2 O's. I've actually got 5 over here, right? 3 and 2, I've got 5, and here I've got 6. Oh.
We're screwed.
What? Let's put, what should I do? Put a 2 there? No? 2 in front of here. I feel like I'm on The Price is Right, and you guys are yelling at me. Put a 2 here. That's what you're saying? Okay. Let's try. I'm so flustered here, I'm gonna try and, I'm gonna start over again.
Erase that other 3.
Okay, erase that 3?
Yes.
Okay.
Oh, this eraser doesn't even erase.
Okay, well, let's start again. Chance, help me out. How many 2's? How many C's?
You got a C there?
How many? I put a 2 in front. 2 C's. And how many O's?
There's
2. Oh, I guess there's a plus sign there, right? So I've got 2 plus 2, I got
4.
4. Easy.
What? So what?
How many O's over here, Chance?
Don't worry.
I am worrying about it. You need 2. How many C's?
1.
Just 1. How am I going to balance them? Oh, now it's,
Two.
put a
Throw
2
in
there.
two. Wow, you made it
There
so
we go.
complicated.
There we go. Right, now it works. You can see that sometimes it's hard. You have to start over again. You might have to, maybe I started in the wrong spot. Did I start in the wrong spot?
Yes.
I think I did. I started in the wrong spot. I tried to make those O's. I should have started with the C's. Sometimes that happens. That's okay. There's the balanced equation. Okay. Try this one on your own. 45 grams of aluminum reacts with bromine gas. Produces 65 grams of aluminum bromide. How much bromine gas is produced? This one question has just about everything I've taught you from February on in here. This is like, if you can do this, you can do everything. Pretty much. It's worded wrong?
Yes, if the bromine gas is
Reacts with bromine gas. Oh, sorry. How much bromine gas was required or needed? You're right. You're right, absolutely. Can I show you this, Jack, so that when I ask you later to do it, I know, you know what to do? Okay. All right, thanks, Wyatt. I missed that one. I just made this up last night, and I missed that. Okay, so I got 45 grams of aluminum. That's right. Whoops. That's right. Aluminum. Bromine gas, is it one of those diatomic ones, Cole?
What?
Is bromine gas one of those diatomic gases that we need? Yes, it is, right? So it's going to be what? Br2. And it's producing 65 grams of aluminum bromide. Now, how do I know? Well, it's going to be Al and Br, but what are the numbers there for aluminum bromide, do you think? Just leave them how they are? As you can see, I don't have my periodic chart yet put up. I need to get Mr. Frederick on that. Where's aluminum?
Sit down. Yeah.
Thank you. Oh, I thought you guys were showing something. Right here, group number
3.
3. And bromine is over here, right?
7.
7, right? Are we talking about an ionic bond here?
Yes.
Yes, we are. Aluminum is a... Maybe I should put it there. Aluminum is a metal. Yeah, I see that. So aluminum is a 3. Let's just do it with a Lewis diagram here. Quick review of Lewis diagrams, Brandon. Aluminum has 3. Bromine has 1, 2, 3, 4, 5, 6, 7. So how many aluminums am I going to need? How many bromines am I going to need to match up with aluminum?
3.
I'm going to need 3. So what's the formula going to be? Al.
Al. 3.
Which one do I need?
Two.
1 goes there. Another Br, right?
BR3.
One goes there, one goes there. Br3, exactly. That's AlBr3. You should know how to do that already.
Oh.
Okay. Now, I've got 45 grams of aluminum. I've got bromine gas, and it gives me 65 grams over here. So what's my answer? How much bromine did I need? 20 grams of bromine. And write the balanced equation. Is this balanced? Uh-oh, here we go again. Are you worried? Are you worried for me that I might not be able to do this one? I have to admit I'm a little bit worried. 1 Al, 1 Al, right? 1, right?
Yes.
Br2,
Oh, this one's easy. Oh,
2, Br, oh geez, here we go again with one of these 2s and 3s. Should I start at the 6 like I did last time?
Yep.
Yeah. Or, no.
Well, I have to, because how am I going to balance the ALs, right? Because there's only one of them. All right, well, let's make this 6 and make it 6, see if it happens. How do I make the one on the right 6? Put a 2 there, right?
Yeah, but not yet.
2 Br3s, now I got 2 ALs. Oh, I can fix that. Put a 2 there.
Oh,
And last one, Mike?
3.
3 there, perfect. Perfect. All right. That, my friends, is it. The end.
Oh, yeah. Oh, dude.